Okay, good morning, or I guess good afternoon for those on the East Coast. To everyone, thanks for joining our webinar today on using life cycle assessment to evaluate the environmental performance of electric vehicles. My name is Mike Centetos. I'm the Policy Director for the National Center for Sustainable Transportation. I'll be moderating the webinar today. This is part of our monthly webinar series that we put on here at the National Center for Sustainable Transportation. And we actually have another one coming up next week on February 3rd on bicycling infrastructure. So check out our website for details on that one. NCST is part of the University Transportation Centers program administered by the U.S. Department of Transportation. It's a consortium of 6 universities around the country focused on advancing environmentally sustainable transportation through cutting-edge research, direct policy engagement, and education of our future leaders. We'd like to invite you to sign up for our mailing list to get notifications about upcoming webinars and our current research at ncst.ucdavis.edu. Today's webinar will last an hour. We'll have a presentation from Dr. Alissa Kendall, followed by guest commentary from Hanjiro Ambrose at the Union of Concerned Scientists. And then we're going to open the floor up for questions and answers. There's a Q&A feature on the Zoom webinar platform. If you look at the kind of the bottom toolbar, you'll see a Q&A button there, and you can type in your question at any time. We'll do our best to answer all of them. We will be recording this webinar, so it'll be available with closed captioning on our website, along with the slides following the presentation. So with that, I'd like to introduce Dr. Alissa Kendall. Alissa is the Professor of Civil and Environmental Engineering at the University of California, Davis. And Alissa, I'll turn it over to you.
Thanks so much. So I'm going to get started by talking about why life cycle assessment might be important, especially as we look out into the future and we start adopting more electric vehicles. And so in the on-road transportation in general, we see trends that really make life cycle assessment more important. So if you look at this chart, pie chart, the one on your left, gasoline, for example, is a conventional fuel that we've depended on for a long time for passenger vehicles. And the combustion or the use of the gasoline has dominated impacts such as greenhouse gas emissions and energy consumption. Likewise, vehicles have been dominated by operational impacts, whether it's air pollution, greenhouse gas emissions, or energy consumption. But as we look at alternative fuels and trends towards electric vehicles that run on electricity and hydrogen, the upstream or life cycle related impacts are increasingly important. And this is true for vehicles as well. So as vehicles move towards electrification, we see increasing dominance of production-related emissions. And that's because these vehicles are more efficient, but also as we decarbonize the grid, we reduce greenhouse gas emissions and many air pollutants as well. So I've used the term life cycle assessment or LCA. And just to clarify what this means, it's a structured environmental assessment method where we quantify environmental flows and their impacts for a product or service from a cradle to grave perspective. So we're tracking material and energy inputs and waste and pollution outputs at each life cycle stage, but we also think about the supply chains that deliver us those material and energy inputs. And we consider transportation at each stage. And also over here on the right, you'll see a term end of life. This is our catch-all for what we try to do with a product at its end of life. And you can see that recycling, remanufacturing, and reuse are all options. And we'll talk a little bit about that for electric vehicles as well. So also another point of clarification, life cycle assessment traditionally considers a whole range of environmental impact categories. But as you'll see, a lot of electric vehicle and automotive assessments in general have really focused on greenhouse gas LCA, which we often refer to as carbon footprint. This is acceptable in a lot of cases when we're really concerned about climate change impacts. But to be clear, if we want to understand the full burden of impacts associated with the technology, for example, we really want to think about multiple environmental impacts so that we don't trade one impact for another. With that said, I'm going to focus on carbon footprints or LCA of greenhouse gas emissions. So a review of previous LCA studies of battery electric vehicles or BEVs have almost uniformly considered small, efficiency-oriented electric vehicles. These are basically modeled on first-generation Nissan Leaf that had approximately 25 kilowatt-hour batteries. Most of these studies found that, or in fact, almost all of them found that the composition of the electricity grid that charges them is crucial to understand their performance. And in addition to that, the climate in which they operate is very important. And because of this, it's really, we really have to think about the spatial and temporal dynamics of where these vehicles are operated and how the grids that they operate on might change over time. In addition to thinking about trends in electricity grids, we also need to think about trends in vehicle design. And this is something that hasn't been considered in previous studies. So if we think about, if we look at this data here, this is sales data starting in 2012 through the first or second quarter of 2019. And what I'm showing in the dashed line up there is the average, essentially battery capacity of what's being sold. And the yellow line above it, or that crosses it, is a sales weighted average of battery capacity sold in any given quarter. And what you can see is that between 2012 and the beginning of 2019, we saw dramatic increases in the average vehicle battery capacity, from about 35 in 2012 all the way up to about 70 in 2019. We also saw big changes in the types of vehicles that were being sold. So the Nissan Leaf is shown in navy blue, and you can see that those small sales in 2012 were dominated by Nissan Leaf. Then we saw the Tesla Model S come online and take a reasonably large share of those sales. But then if we look out to 2018, for example, Tesla Model 3 and the Tesla Model X are all large and important vehicles out there. You also see the Chevy Bolt that came online in yellow there. The reason I'm highlighting these models is that these are very different types of electric vehicles. And we're going to talk about how that can affect what we can say about the life cycle impacts of electric vehicles. Some of this trend in vehicle change can be explained in part by dramatic decreases in battery costs and increasing performance of electric vehicle batteries. So this is a projection of the changing costs of batteries on a per kilowatt hour basis. And the reason I'm showing this is to point out that the trends that we see towards, for example, high performance and large vehicles like the Teslas might be something that we're going to see continuing to happen because we see that the battery costs are coming down. So what happens to our understanding of the life cycle impacts of battery electric vehicles when we account for some of these important trends? So in terms of vehicle design and market trends, with these decreasing battery pack costs, we might see increasing battery pack size, even in efficiency-oriented vehicles, and greater dominance of luxury and high-performance cars in the BEV sector. We might also see the adoption of shared and autonomous vehicles, especially as high-mileage applications are enabled by these larger batteries. In addition, we have electricity fuel mix trends. So as electricity grids decarbonize, especially where BEVs are being adopted fastest, like in California, we see the operation-related impacts of electric vehicles dramatically reduce, but potentially the production-related impacts of these vehicles increase. Okay, so the implication of these trends, likely to be bad, are the fact that large and high-performance electric vehicles mean larger batteries and designs that may not focus on efficiency. And in addition, we might see increasing investment in lightweight materials to deliver on performance and efficiency as well. Likely to be good, an increasing range for these vehicles. So going from, say, 100 miles to 300 miles. And that means that batteries might last a lot longer because they're not being cycled as deeply in terms of a depth of discharge, which is a key deterioration process for batteries, and then reduced barriers to adoption, including in higher mileage operations. And then, so from this, we developed a study where our goal was to conduct sort of a preliminary LCA focusing on production and use of new model and future model BEVs, considering only the most important spatio-temporal dynamics like changing electricity fuel mixes. Our modeling approach for this was to take three what we call archetypal BEVs. So an efficiency-oriented compact vehicle, you can think here Chevy Bolt, a performance luxury sedan, and here you can think Tesla Model S, and a performance SUV, and here you can think Tesla Model X. We use scenarios to explore, in addition, the other trends that we think are going to happen over time. So the trends in terms of the electricity and the difference in space and time, so California versus US average, and then present and future grid mixes, but also some alternative use models, such as shared and autonomous applications. To do this, we combined existing and new LCA models for vehicle components and systems. So we used a battery LCA model from Ambrose and Kendall, but this was actually built on BATPAC, which is a model out of Argonne National Lab. And for our vehicle model, we used GREET, also out of Argonne National Lab. And then we used a number of methods to estimate use phase impacts under different scenarios, including annual mileage estimates from the National Highway Transportation Survey, or NHTS. And then also it used FASTEN, which is a model to try to estimate fuel or energy efficiency of vehicles. Okay, so just as a quick view of how we modeled electricity grid trends, you'll see on the top left here what we call business as usual, and this is essentially the fuel mix for business as usual conditions in California and the US over time. In California, you'll see the navy blue there is the renewable electricity sources, and the yellow is natural gas. So you see a trend towards the dominance of renewables, and the only fossil fuel remaining in the mix being some portion of natural gas. In the US, you see increasing proportions of renewable sources, but you don't see the same trend towards steep reductions in fossil fuels. What this leads to, shown on the bottom right, is the net greenhouse gas emissions factor per kilowatt hour that shows steep reductions in California and only mild reductions for the US average under the business as usual scenario. However, we also tested a carbon tax. This is not because we think a carbon tax is politically feasible, but just to have an optimistic scenario for the national case. On the dashed line there, you see what would happen if we implemented a carbon tax nationally. For California, the carbon tax doesn't have a very big effect because we're already increasing our renewables pretty rapidly, and so I'm not going to show you the results for a carbon tax implemented for California conditions. We also explored a number of vehicle scenarios. So an efficiency-oriented electric vehicle, the high-performance luxury sedan, the high-performance SUV, and then a shared and autonomous vehicle, which has much higher per day mileage traveled, and then longer range versions of these vehicles for 2025, where we explore battery capacity increases of between 40 and 75 kilowatt hours. And I also want to just point out that our benchmark vehicles are an internal combustion engine vehicle, or ICE vehicle, and a hybrid electric vehicle, or HEV. So without too much more explanation, I'm just going to jump into our results. So what you see on this bar chart on the left, a number of vehicle scenarios, and I want to first tell you what the bars mean. So the yellow part is your operation emissions, assuming US average grid. The gray part is your vehicle materials and glider assembly, so vehicle production essentially. And the two blue parts of the bar are battery materials production, and then the battery manufacturing or production itself. Now I'm going to show you the first takeaway, which I think is important to keep in mind, is the fact that compared to ICE and HEV vehicles, our electric vehicles do very well. Okay, so even compared to a hybrid electric vehicle, essentially nearly every case for our electric vehicles perform better, meaning they have fewer emissions per mile. With that said, there are significant differences between the values we see for electric vehicles operated on the average US grid and electric vehicles operated in California. So if we start by talking about the US, we have our US average, our business as usual case with yellow bars, and then the case with the carbon tax with the red X mark, and then for California, the black diamond. What I want to highlight here is that if we think about operating an electric vehicle in California, the vehicle production is in quite a few cases more than half of the impacts. So that's a dramatic change to how we think about impacts happening. If you look up at a light duty vehicle ICE, which is the top bar on this chart, the vehicle production is a very small part of the total life cycle impacts. And so I think it does tell us that we need to maybe shift the way that we think about vehicle impact, especially as we move towards decarbonized grids and electric vehicles. I also want to highlight on the bottom here the shared and autonomous vehicles, or SAVs. The first thing to observe is that there are definitely great benefits to adopting electric vehicles in these applications relative to, for example, an ICE SUV. With that said, I also want to point out that the production-related impacts for the vehicle and the batteries here are much smaller relative to operation, and that's because they're being used a lot every day, right? The other thing I will point out is that relative impacts of vehicle production compared to batteries changes because in these high mileage applications, we have assumed a battery replacement. So the relative contribution of the vehicle production and batteries is slightly different. So the takeaway from this is that it does matter what use case we think about for these vehicles in terms of the proportion of impacts attributable to non-operation emissions, but also that as we operate these vehicles in places like California, the production-related emissions are extremely important for understanding the life cycle impacts of the vehicle. I also want to bring up another point, of which I think also often comes up when we talk about the life cycle impacts of electric vehicles, and that's the end of life for batteries. So the fate and reuse or recycling of potential batteries at their end of life is really quite uncertain, and there's, I think, been a lot of information out there about the potential problems associated with these batteries. So the first thing I want to point out is that there are unlikely to be large greenhouse gas related impacts associated with these end-of-life batteries. And the second thing I want to point out is that there are other environmental impacts that probably are of concern. Like many electronic waste, there are materials, constituent materials that are of concern in here. There are some issues associated with how we understand what's going to happen to these batteries. One of them is that the falling cost of batteries and relatively low value of constituent elements, if we recycle them, present challenges for robust recycling systems. With that said, there are actually a lot of alternatives for how we manage these batteries at end of life. Here I'm borrowing an image from the Resell Center at Argonne, and or led out of Argonne. And we can see here that there are a number of options. There's reuse or cascading uses, so secondary applications. A lot of people envision using these batteries, for example, to provide grid services or to help integrate intermittent renewables on our grid. The next is recycling and refunctionalization, or direct cathode recycling. And these are all different ways where we can actually either recover the materials that are in the battery, or perhaps better yet, essentially directly recycle the cathodes in these batteries and make these batteries functional again, and not lose all of the investment we made in producing the batteries in the first place. And then finally, there is the option of direct disposal, meaning that we don't actually do anything with these batteries. So one of the things to keep in mind about these potential issues is that there are really long lag times in terms of when recycling or reuse of these batteries happen. And the chart I'm showing here is from a previous paper that included a material flow analysis of lithium materials over time. And what I want to focus on here is the blue area, the potential recycled flow. And if you look down at the years, you'll see there's a really long delay before recycled materials might play an important role in essentially, and this is for lithium, which is a key part of lithium-ion batteries. It's going to be a long time till those make an important contribution, those recycled materials, to the total material flow. And that's partly because we have really rapidly increasing demand for batteries. So the amount of material demanded in the future is much higher than now. But we also have the fact that these batteries are going to be in use a pretty long time. And if we put them in secondary uses like grid services, for example, it's even longer. So you're looking at lifetimes of, say, 1 or 2 decades before these batteries become available for recycling. So while the end of life of batteries is an environmental issue, there is some time for us to develop robust reuse and recycling infrastructure or policies to avoid unintended consequences of all of these batteries being retired at the end of life. So some broad discussion of the findings from this work. First of all, some of the key conclusions of those previous studies, those ones that looked at 25 kilowatt hour batteries in something like the original Nissan Leaf are still pretty similar. So where you charge a battery electric vehicle matters. And most of the time, BEVs outperform comparable ICE vehicles from a CO2 equivalent standpoint. The relative contribution of emissions from vehicle and battery production, however, is increasing on a grams per mile basis. And this is a change from those early studies. It also gets more important over time, and that is for two reasons. The first is the decarbonization of electricity grids, but the second is the fact that we're investing in bigger batteries and high-performance vehicles. From this, we might ask an important question, which is, do we need life cycle-based fuel economy or energy efficiency standards to achieve climate mitigation goals from light-duty vehicles? Finally, for the battery end of life, my message is to stay tuned. There's a lot of potential innovations that could occur to address the problem of end of life batteries that are coming on the market, and also policy development that could shape it. So I mentioned the fact that our new findings might really shape or might bring into question whether the way that we manage light-duty vehicles from a policy context is really complete. So right now, we really think about vehicle operation, whether it's tailpipe emissions or fuel efficiency standards. This is what we've, for a long time, used to manage the performance of vehicles on the road. We've also thought about life cycle, but mostly from a fuel cycle perspective, and mostly in the context of, on a federal level in the US, the RFS2, but probably more important from a life cycle perspective, the low carbon fuel standard here in California. But we really haven't come up, or we really haven't faced sort of thinking about the entire vehicle life cycle in a policy context. So one question to ask is whether life cycle-based policies are needed. So by omitting life cycle emissions, could we come up with a paradoxical policy outcome, meaning that we intend to favor vehicles with lower greenhouse gas emissions, but instead favor vehicles with higher emissions? The other question to be asked is whether there are benefits to life cycle-based policies, like flexibility for meeting greenhouse gas targets for vehicles. Of course, one of the big challenges is the fact that a life cycle-based vehicle policy could be really complex, and it could really be hard, to achieve if it weren't developed and managed well. I also want to point out that life cycle-based policies are relevant for internal combustion engine and HEV vehicles as well. And this is an older study, but it looked at the effect of lightweighting on life cycle emissions and showed that there are definitely cases where achieving lower emissions during the operation of a vehicle through lightweighting materials could actually lead to significant increases in life cycle emissions. And here you see the lighter and heavier designs, and it's important to think about what you're actually doing when you're actually trying to achieve total life cycle emissions reductions, even for conventional powertrains. So back to the question about life cycle-based policy, maybe the most important one is, could it be done? So I'm just going to review a few existing policies that incorporate life cycle thinking or use life cycle assessment to think through whether or not we could come up with a vehicle-based life cycle policy. And I'm going to look at experiences from biofuel policy, looking at the environmental product declaration system, which here in the US is probably has been adopted mostly through the LEED building certification system, which I'll talk about. We'll also briefly talk about the end-of-life vehicle directive in Europe. And one thing to keep in mind is also sort of whether eco-labeling schemes could be an alternative for vehicle life cycle policy. So first, I'm going to talk about actual life cycle-based policies. And really, there's only one class of policies that have implemented life cycle carbon accounting or greenhouse gas assessment, and those are the low carbon fuel standards. And in California, these are implemented through essentially a common government provided model that's based on a California version of GREET. And it's used with the option for producers to submit their own calculations for life cycle emissions of their fuels. The reason I'm highlighting how this is implemented is that in this case, the government has defined many of the assumptions that would go into any life cycle assessment. And this is really important because without that kind of common modeling tool or GREET, there'd be a huge amount of flexibility for fuel producers to play around with. So this is directly from the Low Carbon Fuel Standard website, but you can see that these fuel pathways that they've come up with, you can request a fuel pathway to receive a carbon intensity score through the policy. And in this case, what I want to highlight is that the tool provides default carbon intensity estimates, but also the option for producers to request their own carbon intensity scores. But by using this common model and getting approved through a common system, the risk of high variability and a lack of transparency is reduced. In a completely different context, I'm going to talk about LEAD, which is a voluntary program. So the Low Carbon Fuel Standard is not voluntary, but the LEAD program is a green certification program that is voluntary. And what LEAD has done is that it has integrated life cycle assessment through environmental product declarations, or EPDs. The way they've done this is they offer extra points for certification if contractors source their materials with EPDs, meaning that they purchase a material that includes an EPD. Within a short time frame of LEAD doing this, we saw a real explosion of new EPDs for North America focused on construction materials. And the reason this is interesting is it's very influential, but it's also a voluntary certification system. And so this is not implemented by government. It's just a voluntary certification. So I use the term EPD, or Environmental Product Declaration. And EPDs require what's called a product category rule, which define how an LCA is done for a particular product category. And so we would need to develop essentially product category rules for vehicles if we were to envision using these as part of a life cycle-based policy for vehicles. And I'm showing you on the right an example. This is from the American Wood Council, one of their building products. And you can see it's sort of like a label that goes with the product that has a report on the environmental performance of the product using life cycle assessment. So just as a point of cars are really complex systems, okay, very complex. And so one of the ways that we could envision linking EPDs with vehicles is through the kind of labeling that's been done to achieve the end-of-life vehicle directive in Europe, where parts have to be labeled essentially to assist in recovery and recycling. The other thing I want to point out is EPDs are not just about carbon intensity. It is a true LCA in the sense that multiple impact categories are considered. And this is something that life cycle assessment practitioners are concerned with, because we want to make sure we're not causing significant increases in other impact categories in our goal to reduce greenhouse gas emissions. So in terms of EPDs, we could think of them being deployed in different ways. So you could envision a voluntary process to initially build capacity, like LEAD has done for construction materials. You could also think about vehicle policies that award manufacturers credits or particular eco-labels for using materials or products that have EPDs associated with them. And these would be sort of ways to build capacity in the industry for collecting relevant information for these things before implementing them in some sort of strict regulatory environment. And I already talked briefly about Europe's end-of-life directive, but the reason it's a good model for us to think about is that this directive has required the labeling and tracking of parts associated with vehicles. And this would be required as well in any kind of life cycle-based policy, especially if it was associated with a kind of EPD type model. It could also be used in the context of something like the Low Carbon Fuel Standards use of the GREET model, where you would report material type and weight, for example, based on part information, and link it to a centrally managed model. Okay, so what could we conclude from this? First of all, I would say that EPDs for every part would be kind of a wild west at the beginning, but it might also provide for a lot more innovation than a sort of low carbon fuel standard like approach, where you have some centralized model that you use to conduct calculations. On the other hand, that centralized model could guarantee more transparency in calculations and probably more traceable carbon intensity estimates. A perfect scenario might combine the two of these approaches. So EPDs for every part, for example, but consistent underlying data and assumptions to minimize gaming the system and to minimize the risk of very high variability across calculations. Okay, and with that, I'm going to end here. I want to acknowledge the contributors to this work, who include Dr. Hanjiro Ambrose, Dr. Liz Bolton, and students Mark Lozano, Sadnan Wache, and Eric Moroni. I'd like to now present the discussant for this talk, Dr. Hanjiro Ambrose.
Thanks, Alissa.
Thank you, Alissa.
Hanjiro, over to you.
Oh, sorry, Mike. Didn't mean to talk over you there.
Head over to you.
Yeah, absolutely. Sorry, I was just I've been trying to reply to questions during this and some of the discussion, so I'm trying to do that as well. But thank you for the presentation, and I'm obviously being part of this work. I obviously think this is an important issue. Looking forward to think about both the trends in design and technology development, as well as the behavior and use of these technologies in the field. Particularly as we look towards a transportation system that might be increasingly automated or have increasing levels of connectivity. I think this type of perspective is really important. And in this work, I think we did try to incorporate a lot of dynamic trends in the changing vehicles, batteries, and the changing grid. And now I think, we're both, we as a group have all been thinking about how to kind of take a broaden the life cycle perspective on this work, both from an environmental impact standpoint and thinking beyond GHGs, and also thinking up and down the entire value chain of the battery system and the vehicle. And so, I think, if I was gonna, ask Alissa a question about this, I guess, in my mind, it's kind of, what's the next thing that we need to include? I think the policy perspective is really important, but, from a technical analysis or from an environmental analysis, where do you think the next biggest gaps still are in our understanding of the environmental impacts of electrification?
Well, Hanjiro, you really lobbed over a tough question. So that's a great question, though. So I would take two different sort of themes here. One is the fact that we really have focused mostly on greenhouse gas emissions, and we being sort of the research community and policy when we've thought about electric vehicles. And so I think we also need to think carefully about the other primary impacts caused by on-road vehicles. So air pollution is prime among them. And in the case of electric vehicles, in most places, we're going to be reducing those air quality pollutants. But of course, we are also transferring those pollutants to wherever electricity is being generated, especially if it's being generated with fossil fuels that have high amounts of air quality impacts. So I do think that there is a real benefit to doing that. And to do it well, we really need to be even more careful about our spatial modeling. We really need to understand who's affected by tailpipe emissions versus who's affected by electricity generation emissions, or even by the supply chains that are building our vehicles. And to do that fairly, we need to do a good job of modeling both ICE and ICE vehicles or gasoline and diesel vehicles, as well as electric vehicles. So that's part one. That means making sure we don't sort of keep this, singular focus on greenhouse gas emissions without thinking about the other benefits or disbenefits associated with alternative energy pathways for vehicles. The second part is probably, doing a better job of understanding both the supply chains that provide the materials to produce our vehicles, but also what's happening to materials and vehicles at end of life. And that means understanding the fate of batteries, but also just doing a better job for modeling vehicle retirement and any recovery operations that are happening there. And so again, I think that's whenever we think about this for electric vehicles, we have to remember that a lot of the same shortcomings exist in how we model gasoline and diesel vehicles. And so we always need these comparisons to actually be fair, which means that we're implementing these improved modeling processes and techniques across all potential technologies.
Great. Well, I think we're going to transition into the question and answer part of our presentation. Alissa, thanks for the great presentation, and Hanjiro, thanks for your commentary as well. Just a reminder to folks that there's a Q&A button on the bottom toolbar of the Zoom platform, so go ahead and use that. It's a little bit easier for us to keep track of them than the chat window. So we're going to start with a question about emissions from battery production, Alissa, and you talked in your results. It was clear that the battery size was significant in terms of figuring out what the overall life cycle emissions of the vehicle were. So the question is whether the life cycle emissions for battery production are linear. So as battery size increases, is that kind of a linear relationship with emissions? And could you scale those results to batteries of any size?
Yes, and I'll allow this to Hanjiro in a minute. It's not linear in the sense that not all materials used in the battery increase linearly with battery size. So just, for example, a lot of these batteries are encased in aluminum, and as you increase battery capacity, it's not a linear increase in terms of battery casing. So that's just one example of why these are not perfectly linear. But it is definitely true that as we increase battery capacity, all else equal, we're going to increase the impacts associated with producing those batteries.
Yeah, and I tried to give a slightly more nuanced answer in the Q&A to that question, and Alissa's right. Generally, bigger battery, more things, but I don't think it's appropriate to extrapolate linearly from this model or these outputs directly towards, outside of the range of capacities that we assess in this study. Meaning that, you couldn't, just like, most regression, you don't want to go outside the bounds. So, to extrapolate this to a personal mobility device or a heavy duty vehicle like a bus or truck that might have either an order of magnitude smaller or larger capacity of battery, or be at a very different voltage configuration, which is actually maybe the key piece. I don't think it would be appropriate to extrapolate these results. There is some significant changes that occur in battery systems because they are designed for specific applications. So, the modeling that we're doing here is kind of from bottom up, based on electrochemical potential and material properties. And so, it gives us maybe a reasonable way to approximate these types of devices. So I think yes and no. I think, within the range of battery sizes for light duty vehicles, these are probably pretty representative results. For other types of technologies, I think, we would want to think more closely, deeply about the differences in design.
So we've got a couple of questions about, I'll try to kind of summarize in one in terms of uncertainty, in terms of emissions associated with electricity generation on the electric grid. We've got one question about kind of a long time scale and the uncertainty of where the grid's going to go over time. And then another question about how time of day in which charging is done could affect, whether you're getting solar in the middle of the day or maybe more, gas at night. Can you talk a little bit about, I guess, kind of the granularity of this analysis and which of any of those factors were taken into account, and then maybe talk about kind of how that would maybe next steps in terms of trying to capture more of those?
Yeah, sure. So one of our goals, one of the reasons we decided to do a few different electricity scenarios was to explore, what the ramifications are of sort of optimistic or pessimistic futures for what electricity grids will look like. And that's especially true at the national level. So instead of worrying about, for example, like a probabilistic approach to understanding uncertainty there, we just tested out a few sort of extreme scenarios to understand what the implications are. And I think it's clear that the implications are that, battery electric vehicles are much more preferable compared to gasoline and diesel if we see these electricity grids decarbonizing. That's kind of an obvious answer, but I think it's important to sort of think about that. The time of day charging is an excellent question. So work that we've done previously even has really considered the issue of what we call marginal demand. So what happens when we demand one more marginal unit of electricity from the grid? And this is not unrelated to the question of sort of intermittent renewables on the grid. And the reason that people have been concerned about that marginal demand is that we're not really good at turning on and off renewables when we need them, right? So if everyone plugs in at night when they get home to charge their electric vehicle, solar panels are not going to be providing the power that people need. This is true for any kind of, for anywhere in the country, regardless of whether they're renewables or not. We have to figure out what is the source of electricity that's going to provide that extra unit of electricity demanded by all these new electric vehicles on the road. And a lot of studies have shown that those are likely to be slightly dirtier than the average grid, whether it's because you're turning up and down a coal-fired power plant in the upper Midwest, or whether you're turning on not very efficient peaker plant in California running natural gas. Now, we did not include that in this particular study. There are two reasons. One, it's really hard, but I mean that in a real way. So a lot of the models that are out there to look at marginal demand, look at historical data, look at historical fuels being supplied, and try to infer what the marginal provider of electricity is. If we see dramatic changes in the makeup of our grid, it is not very easy for us to say what that's going to be. So we could probably have tested out a worst case for California, assuming that natural gas peaker plants are providing that marginal electricity, as an example. So that could be something we could explore. In addition to that, it's really hard to argue that electric vehicles are going to be marginal demanders of electricity if they are all over the road for a while, right? So during this time where we're suddenly ramping up electric vehicles and we're thinking about policies that require electric vehicles to be on the road, it's arguable that these are marginal demanders of electricity, not sort of the existing average demand that's out there. But in the future, in a future that is highly electrified, you know, these electric vehicles are kind of like refrigerators, right? Everyone has one. And so in that sense, I'm not sure that thinking just about electric vehicles being the marginal demand is really sort of the right perspective to have. So those are the two ways to think about the marginal demand issue. And it's true that I think if we did test, given the information we have today about who or what plants are going to be providing that marginal demand, we could definitely look at a worst case scenario for a place like California and say that you know, natural gas peaker plants are going to be providing that electricity, and that of course would make a lot of these electric vehicles look quite a bit worse.
Great, thanks. So we got a couple questions coming in about material use associated with electric vehicles, and you mentioned at the end of your presentation about how this isn't just about greenhouse gases, right? That there are all these potential impacts to account for. So specifically to some of the materials that need to be mined for battery production, how do we account for those types of environmental and also social impacts or potential social impacts from that type of resource extraction, and kind of build that into this comparison of different technologies and things like that?
It's a great question, and a question we've been curious about as well. So the first thing I want to say is that if we are worried about social impacts from minerals being used for batteries, then we need to be worried about social impacts from oil extraction. So that's the first thing. I think there's been sort of a focus on the issues associated with mineral extraction for batteries without sort of the complementary focus on the impacts for mining associated with fossil fuels. So that's part one of my response. But more importantly is sort of the rest of the response, which is information about this. So there have been quite a few studies done on materials used in batteries and electric motors. The first thing to point out is we're very unlikely to run out of these materials. So any kind of critical material perspective that we hear about with respect to these materials really has to do with supply restrictions due to social, political factors, geopolitical factors associated with materials. And some of them have really important consequences for social impact. I think the most obvious is cobalt, where we rely on production, a lot of production from the Democratic Republic of the Congo, or DRC, where there's known sort of child labor issues, and other really important social consequences to understand. So these are important for us to understand. We have done some assessment of lithium, for example, where we found that even as we access less even as we access less attractive resources, meaning they're more expensive to mine, we don't see an enormous increase in environmental impacts, meaning that per unit of production, we don't expect these impacts to increase. But because total production is increasing, the communities where this is happening obviously will suffer greater environmental impacts. So I do think it's important to consider these issues, and it would be great if we could couple our environmental assessment with a social assessment. And there is an area of work called social LCA, but this area has not been particularly well developed. There are lots of issues associated with it. For example, just a lack of data and information to work from. So I'm not sure if I've entirely addressed that issue, but hopefully that's some sort of background to build from.
And I would just pipe in a little bit on this minerals issue. You know, for obviously batteries, like a lot of clean energy technologies, are dependent on a relatively short list of minerals, which are constrained in their geographic deposits, but more importantly, are probably distributed and concentrated in certain places, which cause potential for supply risks. You know, we talked about cobalt. Cobalt is obviously kind of the big story. 60% of the world's cobalt comes out of one region, and almost all of it goes to China for refining. So that kind of creates a bottleneck in the global supply chain for that mineral. And, you know, but there's another opportunity here for, you know, all these things, in particular cobalt, which while there's a lot of cobalt in today's electric vehicle batteries, it's also possible that the electric vehicle batteries in the future will rely on less and less cobalt. That in-use stocks, and in particular, and also consumer electronics, need to be recycled. You know, we currently have really poor recycling of rechargeable portable lithium batteries, which are actually a much more cobalt-rich chemistry compared to EV batteries. And so I think, you know, one area of work that we're working in, or we're engaging in right now, is thinking about how in-use stocks of materials could meet the future demand for materials and potentially displace primary production, and especially primary production, which have these kind of difficult to quantify and almost difficult to enumerate impacts on communities and people that don't have any capability to adapt or mitigate those impacts. And so I think that can give us some idea of how to technically approach this. Obviously, the societal impacts are almost equally important, but difficult to quantify, as Dr. Kendall alluded to.
So that's great. Maybe we could follow up on that, because we got a question about recycling of batteries and end-of-life issues, and concern about recycling industries for other materials struggling in rather high-profile ways lately. Can either of you talk a little bit more about kind of just where we're at in terms of building a market for recycling batteries, and kind of what it's going to take to get to what you were just talking about, Hanjiro?
Yeah. Alissa, would you like me to dive in?
Sure.
So yeah, I mean, there is commercial recycling of lithium-ion batteries today, but at a relatively small scale. There's actually a commercial recycler in California, but the main two are in British Columbia and in Belgium. And so there are processes that are commercialized today to recover some of the valuable constituent minerals from a battery. But there's also a lot of work to be done on recycling technology development. As Dr. Kendall alluded, there's different pathways potentially we can envision for processing batteries, and all of those pathways have a number of different potential processes, and some overlap. And I think the main goal is that we could avoid some of the additional inputs of energy and reagents in the supply chain of batteries, and that mainly means refining and synthesis of cathode materials. And so, you know, as far as recycling, I think the goal is going to be to try and create recycling programs that are or recycling technologies that are more optimized to recover materials in a more valuable form. So not in a a reduced form where possibly it's the contaminated mineral and it needs to be resynthesized and then refined and then resynthesized into a cathode compound. For that, I think we have a long way to go. One of the big barriers is that we don't really have a lot of policy in place. Current policy around recycling of batteries is mostly focused on smaller portable batteries. We also have a challenge in that there's a diversity of battery types and chemistries across manufacturers, and that mixed chemistry waste stream, all the different types of lithium chemistries, is a barrier to more tailored recycling programs because it's hard to optimize your recovery process to get the most cobalt out or the most lithium out or nickel out or cathode material if you have different cathode materials going into the process. And already we're having issues. I hear from handlers, vehicle salvage yards and scrap yards that are having a lot of issues with lithium batteries causing thermal events, also known as fires, and issues with scrapping, and lots of, and also starting to come in and pollute the supply of used hybrid batteries, which were nickel metal hydride based. So we're hearing reports from people about that being an issue. So I guess my sum story is that we have recycling, and that's a good start. We have a long way to go to develop the necessary recycling, and there are significant policy barriers and some technical barriers as well to creating a robust recycling system in the U.S.
But to end on an optimistic note, we're sort of starting slow, and these batteries are large. It's not like the battery in your cell phone, that can be put in the garbage and no one's going to notice. So I think one of the potential benefits of sort of starting slow with electric vehicles is that we do have a little bit of time to set up better policies and guidelines to make sure that there is management of these batteries at end of life and hopefully a robust process for determining what the best use of those batteries are. I saw another question about the fact that batteries not used in vehicle applications, like batteries used for electric power, is like a Tesla's Powerwall, that kind of thing, that these duty cycles are much less challenging for a battery. And the answer is yes. And again, it's another opportunity to think about what the fate of these end-of-life batteries should be or can be. And it's not just about recycling, but it's about figuring out what we can do, what value we can get out of them at end of life as well.
Great. So we got a question about how can we ensure that LCAs for vehicles and components are comparable when there are all kinds of different databases for material data sets. They mentioned the GREET model, EcoInvent, a couple others I'm not familiar with.
Yeah, that's an excellent question. And I think anybody that has been a consumer of LCAs or a practitioner of LCAs knows that what data set you use for your reference lifecycle inventories is really crucial. These reference lifecycle inventories define the impacts associated with, for example, a material that you're using or a process that you're undertaking. And I think probably the honest answer is that if we're going to do this kind of assessment in a policy context, we probably do need to have an agreed upon database that everyone shares. And if there are very specific changes to how a material is produced or sourced that need to be reflected in there, it'll have to go through something like a pathway analysis for approval, and then be integrated into the modeling tool. So I do think that we do need sort of like an agreed upon database of lifecycle inventories that need to change over time, but need to reflect spatial and temporal change, but that need to be shared across all of these models. And that, to my mind, that's likely to be the sort of best case for how we would avoid some of these problems.
And also, one of the great things about maybe implementing an EPD or Environmental Product Declaration Product Category Rule type system or something like that is that you might be able to build this type of knowledge by having a policy that's disclosure kind of based and really about building capacity for the companies themselves. That also can help us create a standard. I mean, that's to some extent, the LCFS has yielded that, where we have a lot more data on the carbon intensity of different types of fuels.
Yeah.
So just a couple more questions here before we wrap up. We did get a question about kind of the vehicle miles traveled versus passenger miles traveled dynamic, and whether life cycle assessment could be used as a tool to kind of capture the difference between an autonomous vehicle with nobody in the vehicle versus a high occupancy vehicle or something like that.
Yeah, that's a really excellent question. I do think that if we think about new use models, our whole perspective of vehicle miles traveled might be a bit flawed. And I want to give props and hand this over to Hanjiro, who I think has thought about this for quite some time, about whether our grams per mile on a vehicle basis might not really be applicable if vehicles are being used in shared applications, essentially. So Hanjiro, I don't know if you want to add a little bit more to that.
Yeah, I mean, I really appreciate the question. I think this is a good point because, when LCA, we talk a lot about the function of the product and the performance that it delivers. That's part and parcel to the LCA and what we call the functional unit. And obviously the function of a vehicle is not to move itself, but usually to move the people or things inside of it. And so when we talk about per mile, we kind of maybe are missing the point of a vehicle, which isn't necessarily just to realize miles, but actually to move people. So I appreciate this line of thinking. I responded to a few questions in the chat about this, so I'll just go over it for a second. We did use the National Household Transportation Survey, the most recent NHTS data, to estimate the annual vehicle miles traveled by vehicles of different types and different ages. And then we used scrappage rates for vehicle types from NADA, can't remember the name of that acronym, but to get the scrappage rates, basically the number of vehicles, the percentage of vehicles of any model year that are retired in that model year. And so if you combine those two things together, you can estimate the lifetime miles traveled of a vehicle, and you can also look at the annual miles traveled to think about how that intersects with the changing electricity grid. As far as vehicle occupancy, we didn't really deal with that. In the SAV scenarios, what we are assuming are some fixed percentages, or actually decreasing percentages, for the performance of the vehicle, meaning how much of the time it's driving in service or how much time it's out for maintenance, let's say, and also how much of the miles it's realizing are actually are deadheading or not. Just for an emissions calculation. But when we show the LCA results, all that folds into a per mile emissions rate. I do plan to continue to do some work in this area. I do think this is a really interesting area of work to be doing. And I think that, for an LCA, it's going to be important for us to think about, when we talk about transportation LCA going forward, to actually think about both the vehicle moving, but also the function of the people it's moving. Particularly as the use cases change.
All right, well, just in our final couple minutes here, we'll try to tackle one last question. There's a lot of interest in other vehicle and fuel technologies, like hydrogen fuel cells, biofuels, that I understand weren't part of this study, but maybe either of you could talk a little bit about whether there are any future plans for tackling some of those other technologies, or how you think the calculus might change a little bit for some of those other technologies.
Yeah, well, I mean, I think, I don't know if it's sort of, I don't know. I think we see that the primary pathway for light duty vehicles to electrify is through batteries and not fuel cells. That doesn't mean fuel cells won't actually play potentially a very important role in electrifying some sectors of on-road transport. And I do think it's important to look at that. And it is important to think about how hydrogen might be produced in the future, because right now hydrogen is usually produced from natural gas, but if we are able to leverage power to gas technologies and things like that, and make use of potentially curtailed renewables, then hydrogen pathways might be really important parts of a really low carbon transportation system. So again, that one in particular, I think it's not that fuel cells don't have any role to play, but they're not going to be the largest player at all in the light duty sector. And in terms of biofuels, we've done really extensive work on biofuels, and of course, in the context of this kind of assessment, it really would play out by us thinking about substituting some part of gasoline or diesel fuels with biofuels, and we could do that. I think what we have found, however, is that there are very few scenarios where there's large quantities of biofuels that lead to deep reductions in carbon intensity. And the reason I say that is that those fuels that we do have should probably in the future be reserved for applications where we really need liquid transportation fuels. And so I think that's a really interesting future to explore, whether that's for use in aircraft or in long-haul trucking. You know, these applications where we really don't see, especially batteries, playing an important role. I think it is really fascinating to think about what the role of these ultra-low carbon biofuels might be, acknowledging the fact that they are not going to be very large in quantity, since most of our biofuels are still made from purpose-grown terrestrial crops that have other sustainability issues in addition to greenhouse gas emissions.
Great. Well, we're at time here, so I apologize if we didn't get to your question. I want to thank all of our listeners for the really great questions and spurring some really good discussion. And certainly, Alissa and Hanjiro, thank you so much for sharing this great research. So, we had several folks asking that. Just a reminder that the presentation, the slides, and a recording of the presentation will be posted on our website, ncst.ucdavis.edu, the next day or two. And you will also be getting a short survey in your email, which we'd really appreciate if you're willing to share your thoughts on how we can continue to improve. So thanks, everybody. Really appreciate your participation.